Welcome to my YouTube channel. In this video, we are going to learn the concept of the Lenz law. But before we study the Lenz law, we need to first of all understand the Faraday's law of induction. And the Faraday's law of induction is given by this formula: E equal to N d phi B dt, where this phi here is a magnetic flux. And because we have flux in electric field, we also have flux in magnetic field. So to distinguish between the flux in electric field and flux in magnetic field, we use B to represent flux in magnetic field. Now, if you notice here, this equation is not complete. So make justice to that so that we'll see the complete form of this equation. E here is the induced EMF. Phi here is the magnetic flux. Then phi B is equal to BA, where B is the magnetic flux density, A is the area. Okay, so looking at this slide, we notice a magnet has a south pole and a north pole, and that we have magnetic field lines coming out of the north pole. This is the loop at T1 in which the magnetic field lines goes through. So when the loop is moved towards this point at T2, you notice we have more magnetic field lines cutting across it. So at T1, lesser magnetic field lines, at T2, more magnetic field lines. So we'll move to this diagram below to distinguish between the two of them. This shorter arm is the magnetic field flux at T1, and for this longer arm, we have magnetic flux at T2. Because it's a vector quantity, the difference between this and this gives this particular, which is change in flux B. So, because we know from Faraday's law that there will be induced EMF in this loop. Now, the question is, how do we know the direction of the induced current? Should it go like this, or should it go like this? Now, let's consider the first scenario, where we assume that the current should go in this direction. As the induced current should go in this direction. We know that once current is moving through a loop, probably a circular loop, there will be what? Magnetic field generated. So that magnetic field going through this loop will also what? Cause what? A magnetic flux, which is given by this one. So this particular expression here is called the what? The magnetic flux, induced magnetic flux, induced magnetic flux. Now you see the direction of the arrow. Now, when the current goes through in this direction, we tend to use our right hand rule. So the direction of the magnetic field will point downward, which will give us this one. So what you notice is that the magnetic flux points downward, while this one also points downward. So they are going to support each other. Now, because they are going to support each other, they will in turn generate another induced current, which will be greater than this one. And this induced current that will be generated, that is greater than this, when it flows in this direction, will generate another higher value of this one, magnetic flux. As a result, for every new magnetic flux that is generated, it supports this existing one that is generated from the bar magnet. And as a result, it will continue to increase the induced EMF. And this induced EMF will continue to produce larger value. This one will produce larger induced EMF. And the induced EMF will generate its own magnetic field. And it will continue to generate until this particular one will grow to infinity, which is not the case. So for the first scenario, it will lead to the generation of infinite amount of induced currents, which is not so in reality. So We'll now check the second scenario. The second scenario is when the current is going in this direction. And if this induced current is allowed to go in this direction, the magnetic flux that will be coming out from this induced current will be pointing upward. So you can see it's going like this, then current is pointing upward. So the magnetic flux will point, which will oppose this one. So in so doing, it will prevent this one from increasing. As a result, checkmating this particular value. Now, this will not lead to infinite large induced currents, which is the normal thing you experience in a normal current carrying conductor. Okay. So, hence, the Lenz law states that the direction of any magnetically induced current is such as to oppose the direction of the phenomenon causing it. So, the modified magnetic Faraday's law of induction is now E equal to minus N d phi B dt, where this negative sign is introduced by Lenz to let us know that this induced EMF will always oppose what is causing it. Thank you. I hope this video helps. Please like, share, and subscribe to my YouTube channel.